Hi, welcome to the lecture on three-phase transformers. Here I will ensure you that by the end of this lecture you will be in a position to tell why there is a phase displacement of 0 degrees, 180 degrees or 180 degrees plus or minus 30 degrees or plus or minus 30 degrees. And the most confusing topic from three-phase transformers is phasor diagram of star, zigzag star connection and delta zigzag star connection, and that confusion will get clear. Means you will master in the phasor diagram of star, zigzag star and delta zigzag star phasor diagrams. So here are the contents of this video on three-phase transformers. First, importance of three-phase transformers, and then differences between single phase 3 transformer bank and three-phase transformer and core construction and three-phase transformer winding connections. And in this topic we will discuss the important concept vector groups. With the help of vector groups we are going to say why there is a phase displacement of 0 degrees, 180 degrees, 180 plus or minus 30 degrees etc. for the different winding connections, that is delta delta, star delta or etc. And from this topic along with vector groups we are going to discuss the important special winding connections, that is open delta connections and Scott connections. And finally a special concept called three winding transformer will be discussed, and in this about tertiary winding will be discussed. But to understand transformers, knowledge on single phase transformer and three phase circuits and dot convention and harmonics is very essential. To understand three phase transformers, knowledge on these topics is very essential. Coming to single phase transformers, this is already discussed and you are suggested to go through my lecture videos on single phase transformers. What are the basic principles that discussed in single phase transformers also applies to three phase transformers, and it is very important to know the equivalent circuit of single phase transformer to understand three phase transformers. And now coming to three phase circuits, the phase and line relations of voltages and currents for star circuit and delta circuits is very essential to understand three phase transformers. That is, if suppose this is star connection, what you must know is phase voltage is voltage across any phase, that is voltage across any winding. Let us suppose the terminals be R, Y and B and the neutral point be N. So the voltage across this winding or this winding or this winding is called phase voltage. So that we are representing with VR, Vy and Vb, and each phase will differ by an angle of 120 degrees, that is VR is taken as reference, so VR at an angle 0 degrees and Vy at an angle minus 120 degrees and Vb at an angle minus 240 degrees with respect to VR. And the fundamental property is that vector sum of the phase voltages is 0 and the voltages taken across any 2 points, that is voltage taken between R and Y or voltage taken between Y and B or voltage taken between B and R is called line voltage, and that is represented with VRY or VYB or VBR. Here in star connection, the relation between line voltage and phase voltage is V line voltage is equal to root 3 times V phase, and you must remember that line voltage leads by an angle 30 degrees with respect to its phase voltage. This is one more important point that you must keep in mind in case of star connection. And coming to the case of current, the current flowing in any winding is called phase current, and let us represent that with IR. And if you observe that the same current will flow through this line, means in star connection line current is equal to phase current. So these are the important relations that you must keep in mind in case of star connection. And now coming to delta connection. Let us suppose the terminals be R, Y and B, and we define that phase voltage is the voltage across any phase, that is voltage across any winding, and line voltage means the voltage taken between any two terminals. So if you observe in delta connection, the voltage taken between these two terminals is same when compared with the voltage applied across this winding. Means in delta connection, line voltage is equal to phase voltage. And now coming to case of current, if you observe that if suppose the current flowing through this winding be IR and the current flowing through this winding be IB and the current flowing through this winding be IY. So now apply KCL here, and which implies that line current is equal to vector sum of IR and IB, and the relation between line current and phase current is obtained by drawing the phasor diagram, and which will give you that line current is equal to root 3 times phase current. And the important point that you must keep in mind here is that line current lags by an angle of 30 degrees with respect to its phase current. Now let's discuss dot convention concept. Which is used to assign correct polarity to mutual induced EMFs between two mutually coupled coils. That is, dot convention is used to assign polarity to mutual induced EMFs between two mutual coupled coils. That is, whether the mutual induced EMF is positive or negative, that can be decided by dot convention. That is, if current enters on dot ends of mutual coupled coils, then the mutual induced EMF is of positive polarity. That is, if suppose this is one coil, and let us suppose this is second coil, and let us suppose these two are joined like this, and let this coil is having dot end here, and let this coil is having dot end here, and let us suppose current is entering from this side. So observe that here current is entering in this coil on dot end of the coil, and similarly observe this coil here also current is entering on dot end of the coil. So the mutual induced EMF between these two coils is having positive polarity. And this can also be stated in other way, that is, if current leaves on non-dot ends of the two mutual coupled coils, then the polarity of induced EMF between these two coils is of positive polarity. And similarly, if current enters on dot end of one coil and current enters on non-dot end of other coil, then mutual induced EMF is of negative polarity. That is, if suppose this is one coil and let us suppose this is second coil, and let this coil is having dot end here and let this coil is having dot end here, and let this be the direction of current. So observe that here current is entering in this coil on dot end, and similarly here current is leaving on dot end of this coil, means here the polarity of mutual induced EMF is negative. And here you can add or vice versa, that is, if current enters on non-dot end of one coil and current enters on dot end of other coil, then in this case also the mutual induced EMF is negative. If these statements are confusing, then there is simple way to remember this. So these are the cases for positive mutual induced EMF, and these two are the cases of negative mutual induced EMF. And observe that here in case of positive mutual induced EMF, here the two coil ends, means non-dot end and dot ends are connected. And observe here also non-dot and dot end coils are connected. So if dot end and non-dot end of two coils are connected, then in that case the mutual induced EMF is positive. And observe that here if two non-dot ends of two coils are connected, or if two dot ends of two coils are connected, then in this case the mutual induced EMF will have negative polarity. This is simple way to remember. Now I will tell you the importance of dot convention. That is, we suppose this is one coil and let us suppose this is the second coil, and let these coils are joined like this, and let the current direction is towards this side. And now if it is asked to find the mutual induced EMF polarity, then we have to apply right hand rule, and then we have to find the flux direction, and then we have to decide the mutual induced EMF polarity. And in this case, hold this coil with your right hand such that thumb direction is along the direction of current, and the four fingers curl direction will indicate the direction of flux. So the flux direction will be like this, and similarly current direction is towards this side. So imagine that you are holding this coil with your right hand and placing such that thumb is along the direction of current, then the curl fingers direction, that is all the four fingers direction, will indicate the direction of flux. So here the flux directions are same, means here the both fluxes are AD, means here the mutual induced EMF is having positive polarity. And similarly, if suppose this is one coil and let us suppose this is the other coil, and if now these two coils are connected like this, here the coils are same but the way of connection is different, that is the winding sense is different, and let us suppose the current direction is same. Now if it is asked to find the mutual induced EMF polarity, so we have to apply again right hand rule, and find the direction of flux. So this is the direction of flux, and now coming to this case, current direction is now towards this side because the winding sense is different. Now imagine that you are holding this coil such that thumb is along the direction of current, then the four fingers curl direction represents the direction of flux. So here the flux direction will be like this. Now both these fluxes are subtractive, means here the mutual induced EMF is having negative polarity. And the importance of dot convention is that if the dots are present on these coils, then without the help of applying the right hand rule, we can find the mutual induced EMF polarity. That is, if suppose this is one coil and this is the other coil and these are connected like this, and now if dots are present on these ends and if current is entering like this, so observe that current is entering on dot end of this coil, and here also current is entering on dot end of this coil, means here the mutual induced EMF is positive polarity. And similarly, if this coil is having dot end here and this coil is having dot end here, so observe that here current is entering on dot end of this coil and current is entering on non-dot end of this coil, means here the mutual induced EMF polarity is negative. That is, just by observing that here non-dot end and dot ends are connected means positive polarity, and two non-dot ends are connected means negative polarity, or if two dot ends are connected, in that case also we will get negative polarity. So to find the polarity of mutual induced EMF, here there is no necessity of knowing the sense of the winding, and that you can understand with the example of transformer. Let us suppose this is single phase transformer, and in power systems, for the transformer action to take place, we need the primary winding flux and secondary winding flux in opposite directions. Means by applying right hand rule, just find out the flux direction that will be towards this side, and in this case apply right hand rule, and that flux direction will be towards this side, means here flux directions are in opposite direction, means here fluxes are in opposite direction, means the mutual induced EMF is having negative polarity. So is why you can say that single phase transformer is a negative coupled circuit. And now if suppose the schematic diagram of single phase transformer is given, and we know that current directions will be like this, and here there are no information of dots, and if it is asked to find the mutual induced EMF polarity, then how to find? Here we found the mutual induced EMF polarity by applying right hand rule, and that right hand rule we can apply if we know the sense of the winding. Here sense of the winding is clockwise, so the mutual induced EMF we found because here we know the winding sense, as we are having no information about the winding sense, so here we can't find the mutual induced EMF polarity. If suppose dots are given like this, then simply here observe that here current is entering on dot end of this coil and current is leaving on dot end of this coil, means here the mutual induced EMF is of negative polarity. So with this example you can clearly understand the importance of dot convention. So if dots are present, then there is no necessity of knowing the winding sense. We can simply find the polarity of mutual induced EMF. And this concept of dot convention is very important in case of three-phase transformers, because in parallel operation we need to connect the correct polarity terminals. If we didn't connect the correct polarity terminals, then the circulating currents might flow and it might result to dead short circuit. And now coming to the concept of harmonics, the most important one that you must know from the harmonics concept is about triplent harmonics. Also called co-phasals, or also called zero sequence harmonics. Triplent harmonics means odd harmonics which are multiple of 3, means 3, 9, 15 and etc. are the triplent harmonics. And why triplent harmonics are called zero sequence harmonics means they will have a phase angle difference of 0 between each other, and this you can understand from Fourier analysis. According to Fourier analysis, every non-sinusoidal signal is considered as summation of sinusoidal signals of different frequencies, which means that is equal to fundamental signal plus sinusoidal signal of frequency 2 omega and sinusoidal signal of frequency 3 omega and sinusoidal signal of frequency 4 omega t, which means non-sinusoidal signal is considered as the summation of fundamental signal and sinusoidal signal of different frequencies, and of these even harmonics are not considered. Because of their symmetry, there will be no even harmonics, means the harmonics which are present are only odd harmonics. So this is our required signal, and along with this we are having odd harmonics, and odd harmonics are of order here 3, 5, 7, 9, etc. And of these, the frequencies which are multiple of 3 are called triplent harmonics. So because of these odd harmonics, our fundamental signal, that is our pure sinusoidal signal, is becoming non-sinusoidal, which is not desired. So to get pure sinusoidal signal, we have to eliminate these odd harmonics, that is especially triplent harmonics. Why means, if suppose this is the induced EMF in the alternator, so we will have along with induced EMF fundamental signal and triplent harmonics, and the power from the star connected alternator is being transmitted and finally distributed to the load, and let the load be of star connected one. So in induced EMF we will have fundamental and odd harmonics, and similarly in this winding we will have fundamental and odd harmonics. And we know that in 3-phase the fundamental signals will have a phase difference of 120 degrees, that is ER at an angle 0 and EY at an angle minus 120 and EB at an angle minus 240. But now coming to this triplent harmonics, that is zero sequence harmonics. So zero sequence harmonics are having phase difference of 0 degrees, means all the triplent harmonics will start at same time, means triplent harmonic from this and triplent harmonic from this and triplent harmonic from this will start at same instant. So they will start at same instant and they will reach here, and one triplent harmonic is opposed by other harmonics, means for triplent harmonics there is no closed path to flow, means triplent harmonics will remain in the phases. There are no triplent harmonics in lines because there is no closed path, and whereas other harmonics will have different phase angle differences, means they will take closed path and they will flow. But whereas coming to triplent harmonics, as the phase sequence is 0, so triplent harmonics will remain in the phases, and because of the triplent harmonics our fundamental induced EMF is becoming non-sinusoidal. So here our aim is to first eliminate the or reduce the triplent harmonics in the phase. So how can we reduce the triplent harmonics? Means in star connection, by providing neutral connection we are providing path to the third order harmonics, means now third harmonics will flow through the neutral connection, and here only our fundamental induced EMF will remain, means here the generated EMF is pure sinusoidal signal, which is the required one. In 3-phase transformers we will come across the concept of triplent harmonics. So to understand that, we need all these concepts. Here I given an outline just to remind you what is important to know or to understand three-phase transformers. To have much detailed information on harmonics, please go through my videos on harmonics in alternator lecture videos.